Okay, on to chapter 14. So for this one, we're going to be talking about what are called conjugated double bonds, stuff like that. And so this is where you have multiple double bonds, but in an arrangement of alternating double and single bonds. So it's a double, single, on, and on down the way, and stuff like that. And so it turns out that it actually has this sort of stabilizing effect. So if you just have two double bonds in a molecule that are sort of far apart, they just act like two double bonds, stuff like that. But if they're in this, and we sort of see this for the overall stability, it's right where we would expect. But if you put those double bonds in close proximities to where they're conjugated, so double, single, double, with that, so on down, and so that you actually get this added stability to this. Something like that, and it was actually over just having two double bonds, something like that. And it turns out the reason is because if you have your sort of think about your sort of the simplest case here, these are going to be right. So remember, each one of these has an SPPP, right? So like that. So if you have a double bond, right, this is going to be sp2 hybrids. Right, so these black bonds are the sp2 hybrids, but there's also this unhybridized pi orbital here, so that's just going to remain just like a p, right? So with that, so we'll leave that there. This carbon is also going to have there, right? And so what can happen is you have the overlap here, so with that, so of your pi bond. What happens is if you have, say, so these guys in double bond. These guys have, so if there's a double bond here and here, right, and then you have another set of double bonds here and here, notice how there's a nice string of pi orbitals here, so each one, you can sort of think about putting double bond in each one, so you get overlap here and here, but the way that these pi orbitals are sort of shaped is that you can have it so that they're all sort of interacting with each other, so here, here, and here, so it sort of smears across the carbon chain, stuff like that, and that provides a significant amount of stability to the molecule, where you have all these sort of pi orbitals, the p orbitals for the pi bonds, all in a row, stuff like that. So, okay, so like that, and that has some pretty significant consequences moving forward. So like that, because if you have just a, regular alkene, so right, so HCl, right, you're going to have, it's going to follow Markovnikov's rules, right? The Cl is going to go on the more stable, right, because you go through this intermediate step here where the H goes there, and then the chlorine's going to contact, and the chlorine's going to go on the more substituted side. No worries, right? You need to make the more stable carbocation, right? There you go. You're still going to do that, right? And if you have two bonds that are distant from each other, they're going to act just independently, and they're going to both follow Markovnikov's rules. The problem comes when you have these things in conjugation, because as soon as you make that carbocation, right, now you can do resonance stabilization throughout the molecule, so like that, and so you run this here, and things get all sorts of crazy, right? So you run a conjugated diene. Stuff like that with HBr. Now it's not just following Markovnikov's rules, although it did here, right? So if you added the double bond there, you would get it. That's following Markovnikov's. But you also have it where, now the double bond's between carbon 2 and carbon 3, and then the bromine's at the end, which certainly would not be Markovnikov's rules, stuff like that. And so things get complicated in a hurry. And the reason being is because when you come in here, as soon as you form the carbocation, right, it's going to want to form so you're going to want to form this carbocation. Right, so if you have this molecule here, right, and in here, I'll show all the hydrogens. And if you're adding HBr, let's see, you're adding HBr, right? What's going to happen is, right, so this double bond is going to come here and attack there, push that away to form and here's the new H that's added, but we also added we also have a positive charge there, right, because this carbon only has 3 bonds now. And so what can happen is you can do a resonance structure where this moves over there, right, to form this. Right, so now that hydrogen's still there, but now the positive charge is there. Okay, and so when your chlorine comes in, right, because you also make Cl minus, right, if it if it's attacking there, right, you end up with this molecule. Oh, I'm sorry, it was a bromine. The bromine's there, right? Or if it attacked here, right, then you would end up with the bromine there, right? So the hydrogen that you added would still be added here, right? It's just what happens is you end up with this. You try to you add the hydrogen on one side, and it's going to want to put the carbocation right on the more stable spot, which would be right next to that double bond. The problem is now you can move that charge around by moving these electrons, and so you end up with two rather crazy products here, stuff like that. So, and actually you would get attack on this side too, but it ends up getting the same products, stuff like that. And so and that's actually what we're going to cover here. I'm going to change this slide slightly so that you'll be able to see what's going on. So let's say we put a cyclopropane here, here and here, there. So let's do that to be able to differentiate. Actually, let's do it this way. All right. Plus this HBr, right? So we're going to add in this case, I guess HCl. Okay, and so in this case, we're actually going to get 4 products out. Okay, so the first one's going to happen, right? So this goes in, right? Attacks that, moves that over, and so you end up with this there. Right, so you end up getting that product. Oop, not that. You end up getting a hydrogen here. Sorry, that goes there, right? Plus Cl minus. Right? Now you can get this coming over there, right, to form this resonance structure. Right, so the original hydrogen was there, right, and now the positive charge is there. Okay. So with that, so now the chlorine can come in and attack either there or there, depending on which product you're forming. Okay, so if you attack there, you would end up with like that. Attack there, you would end up with it's chlorine. Excuse me, chlorine there and chlorine there. Okay, now the alternative thing would be to let's attack at that other double bond, right? Plus HCl. Right? So now we're getting attack from that double bond. Okay? And so now we're getting so the positive charge is there. Right now we're gonna add the hydrogen there. Right, so we put that positive charge again right next to this hydrogen, because we can form this resonance structure there. Right, this wants to make its 4th bond, so it's going to move the double bond over there, which kind of screws this carbon here, right? So there's hydrogen here, there's a plus charge there. So when your chlorine comes in, right, if it's either going to attack there, right, or it's going to attack there. Right, so hydrogen was added there. The chlorine's going to add where it originally was, or it can form put the chlorine there. And here you've got these 4 different products, stuff like that. So, what you would form with the other one, what you would form with this one, you could do the same thing, but the molecules are actually the same because they're symmetrical, stuff like that. So here are the four products that you would form. So there and there. Okay, stuff like that. So okay, so the next step is what's called kinetic control versus thermodynamic control and stuff like that. And so what happens is, so let's say you have these two products that form the 1,2 and the 1,4. At low temperature, you're actually going to favor this product. Okay, you notice that you favor this product, but at higher temperatures, you're actually favoring the formation of that product. Okay, and so there's actually two different things in control here. There's actually the activation energy. So how much energy does it take to make the product? Okay, so like that. So and then also the other issue is the relative overall sort of stability of the products, right? So what you really want to do is you really want to get as low as possible, stuff like that. And so this would be thermodynamically being at C here at the lowest energy possible. That's the best thing. But the problem is, if you have too high a hill to climb, so that you may not be able to get to C. And so what you can do is you can go to this alternate route where it's a lower hill, right? But it's also it's not quite as low energy. But you take what you can get, and so the reaction takes what it can get. So at low energy, right, where it only has enough energy to get over this one hill, so like that, you'll end up with B, stuff like that. And it'll get what it can. If you heat it up to give it more energy, now it can go in and get over the hill to be able to do this. And so at low temperatures, right? So the kinetic control, this is going to be the one that dominates is going to be the product under kinetic control. At higher temperatures is going to be the thermodynamic control, or thermodynamically favored product. Okay, stuff like that. And so this one doesn't, so this one forms because it's not, it's just not a high barrier to go over. Like that. So like that. So the next thing, so like that. So just a simple concept. Like that. So the next set of reactions we're actually dealing with this, what are called the Diels-Alder cycloaddition reactions. So this is a nice way of forming new cyclohexane rings. So like that. And what they noticed is that when you have a conjugated double bond like this, so to a skeletal structure, right? So that's there, and if you mixed it with just another double bond like that, what can happen is you get this six-membered ring. So with that, what will happen is that'll attack there, this will attack that carbon, and that moves there. And so what ends up happening is you end up with this product. So like that. So here's your 6, right? So there's those 6, and then here's the 2 from the ring. Right? So here's the 4 carbons from this side. 1, 2, 3, 4. 1, 2, 3, 4. And then here's the 2 carbons from this side, right? Doesn't go there, it goes there. So like that. So it ends up there. So like that. So sorry about that. So with that, so you end up with an alkene, right? But the big thing is you form the cyclohexane. So with that, or cyclohexene. So with that, and this reaction works pretty well. So with that, so Otto Diels and Kurt Alder, they were two different labs. They worked together to develop this. So with that, and so this is what's going on, right? So one of these attacks here, one of those attacks there, and that goes up there, and so you end up with this cyclohexane ring. So picture here, with that. So. Okay, so this is called, right, so this is a diene, right, because it's 2 double bonds, right, but this is what's called the dienophile, stuff like that. So this is loving some diene, stuff like that. So it's just basically a regular alkene. You can also get alkynes to do this as well, and stuff like that. And so what you actually want to have this working here, you want to put as much electron density in here, right, and you want this to be, right, so like that. So the what is it? You want this to be you want this to have low electron density, and so what will happen is, right, so you have this, and so you want some, right, so in this case, right, so this is going to be right, the oxygen is more negative than the carbon here, and so what's going to happen is right? So this is going to be positive charge, and so what's happening is the electron density is sort of getting swooped this way, away from this double bond, and to be able to satisfy the electron needs for this carbon here, and stuff like that. And so what you want is you want this here to be sort of electron, have low electrons. You want to have electron withdrawing groups on here, stuff like that. And so your diene can come in here, right? So like that. So your knight's in distress here. It's losing electrons. So your maiden can come in here and save the day, and give it the electron density it needs to form your new cyclohexane here. Stuff like that. So you want a lot of electron density here. You don't want very much electron density here because you have electron withdrawing groups, and you're going to form your cyclohexane. Cyclohexene is technically. Okay, stuff like that. So. And stuff like that. So stereochemistry. So this is one of the powers of this, is you can actually get some pretty nice stereochemical control on this. Okay, and so what'll happen is, so you have your diene here, you have your dienophile. Okay, so it turns out OCH. So for here, right, you got a nice electron withdrawing group here, and you have a methyl. Let's say a methyl on this side, right? I'm going to put these hydrogens in red. It turns out that things that are on one side of the dienophile, right, are going to go one way, either up or down. It doesn't matter. In this case, it doesn't matter. And so what will happen is, so the things on this side, we're going to say those are going to go up. Okay? If those are going to go up, then we're going to say these things go down. Okay? When we make the new. So with that, so here we go. So we're going to do our shifting. So don't forget your double bond over here. Okay, and so what happens is we're going to say if this group goes up, right, that means this group goes up too. That means these two guys on this side of the dienophile are going to go down. Like that. And so here's the stereochemistry of this product. Okay, in this case, it was the opposite, right? It said these two guys were going down, and then these two guys were going up. But again, we're just doing a slightly different enantiomer. So we're doing the opposite enantiomer. Now, if we're going to have the same dienophile, but instead, right, we put this is the cis, right? If we're going to do this on the trans version of that same dienophile, right? Again, we're going to say, okay, we're going to say these are going to go up, so then that means these are going to go down. Right? So we're going to make it that means we're going to say this side's going up, right? Along with this hydrogen here. But that means these two guys are going down as well. So if these guys are going up, these guys are going down. Like that. Okay, it's this side versus this side of the double bond, or of the dienophile, I should say. Okay, stuff like that. So that's how the stereochemistry goes. Okay, so let's draw the stereo. Right. So let's do the stereochemistry of these guys. Okay. Okay, right, so we're going to have that go there, that go there, that go there, right? But remember, we're going to say, okay, so let's say these go down, right? That means these go up, right? So here we go. Don't forget that double bond, right? So we're going to say those guys are going down. That means these guys are going up. There we go. So let's do the trans version of that, right? So again, oh, can't forget that methyl group there. Right. Again, we're going to say, oop, to keep these consistent. Let's say these are going down, right? That means these guys are going up. Okay, so when we do this, right? Don't forget that double bond there. There's a methyl group here, so that needs to stay there, right? So if we're going to say these guys are going down, that means these guys on this side are going up. There we go. Again, here I drew a different enantiomer, but that's okay. So in this case, it's okay. I'll only need one, and I'll indicate that on an exam that I would only need one enantiomer of this. Stuff like that. So, but that'll work. Stuff like that. So it's a nice way of making a cyclohexane, along with setting some stereochemistry for things that don't have any stereochemistry. Here, you're setting actually 2 stereocenters. So it's pretty nice stuff. Stuff like that. So that's why people are excited about it. Now the problem is that diene, the stereochemistry gets a little more complicated when your diene is not just the gets more complicated, right? So if you have, say, that, you know what the stereochemistry is, but we can make this into a ring, right? So putting a CH2 group here, it still works the same way. The only problem is we need to get this up out of the way. Okay, so usually what I do is I say, okay, I'm going to make this sort of like come up out of the page. Okay, so the problem is now the dienophile is going to have a problem. Okay, it can't attack, right? So here's the diene. It can't attack from the front, from the top, right? Because this CH2 group is in the way, right? We're going to say that CH2 is sort of puckered up like that. And so it's going to have to sort of attack from the bottom. But it turns out that the way that this sort of orients itself is that, pardon my drawing here, so if this CH2 group is coming up like this, right, what actually ends up happening is these double bonds, these double bonds here and those lone pairs sort of orient themselves to be right underneath, right underneath here, so you're getting interaction between these guys here, and sort of like if the double bond is, the diene is up here, the instead of being like this, attacking like this, it actually sort of curls underneath to be sort of underneath like this, stuff like that. Because what you get is you get what's called pi stacking, stuff like that. And so these pi bonds like to interact with these pi bonds, and so it sort of curls around like this. And so what you actually end up getting is only a single product. And so what you're saying is, if this one is down, right, so one side of this is, so if this is down, that means this side is down too, which means these guys are up. Okay, and so what ends up happening is you have, right, so we're going to say this CH2 group is up. That means that this part here, these curl down. Which means the other side, these hydrogens here, curl up. And this is what's called the endo product. If they were to come in like this, it would be what's called the extra product. That's not what's formed. What's happening is it's just this sort of, the diene laying, if you have double bonds or stuff like that on your dienophile, they're going to sort of curl underneath to be sort of to interact with the pi bonds of the diene, stuff like that, and so you end up with this endo product. This is the only one formed, stuff like that. So if this is right, so the CH2 is sort of blocking this one face, and so that means that the dienophile has to come in from the bottom face, stuff like that. And so when it does, it forms and sort of wraps itself around underneath, stuff like that. And so you get this sort of crazy endoform created here, stuff like that. So. Okay, so here we go. So we have our cyclopentadiene, stuff like that. So that's what this is called, right? So we're going to say that's coming up, right? We're going to say that that's where that is. Okay. Okay, so you know it's going to form the normal that there, and that there. But how does the stereochemistry go? If the CH2 group here in the cyclopentadiene is coming up at you, that means that anything that has a double bond in it, on like any side group on this side that has a double bond, is going to go down. So if this is up, that means anything with a double bond is going to be down. So here it knows that there's a double bond there. That means this whole side is going to go down. If that's going down, that means this side is going up. Okay, and so you end up with like that. So here we go. Oh, sorry, it's actually. Let me just start over. So it ends up being that. Okay, and then you end up with, here's the double, right? So here's these two double bond, like here's, right? So 1, 2, 3, 4, 1, 2, 3, 4. Here are the two to make the new cyclohexane, right? 1, 2, 3, 4, 5, 6, right? And when we said that was going underneath, that means this Y is going underneath. That means these two hydrogens are coming up. Like that. Okay, so if this guy is blocking this face, that means this side is curling underneath like that to make the endo product. So here's your product here, stuff like that. So here's your cyclohexane, 1, 2, 3, 4, 5, 6. It just so happens to have the CH2 bridge between the 1 and the 4 here, stuff like that. So there's your product. It's the endo product there. This is how you would look at it if you're kind of looking at it at the side. If you're looking at it from the top, which is sometimes a little easier, it looks like that. So either way, I'll take either drawing. Okay, so one of the things about the diene, right? So we talked about the diene, and this is actually going to help with your models, right? So if you have, right, so for a carbon single bond, you can actually get free rotation. You're actually going to, there's some barrier because you're going to have to break up the conjugation, but it's not horrible, stuff like that. And so what can happen is, you notice how I'm drawing these, they're all sort of like together in this sort of cis configuration, and that's the way they have to be in order to make this the ring, right? So like that, this six-membered ring. If they're in this sort of trans configuration here, this carbon here is going to be too far away to form the cyclohexane here, stuff like that. So it's going to have to rotate, right, to get into this. It's going to have to rotate like this in order to get into that configuration, so we can go move forward. Okay. So what's going to happen is, if you have a diene that can't get into that configuration, either because of the molecule, right? So this one here is stuck. You can't get, unless you break that bond. Unless you break this bond, you can't rip. Actually, I guess it'd be more like this bond here. It's locked into this trans configuration, right? So there's nothing anybody can do. Here, you're going to have these two hydrogens, or these two methyl groups, pointing at each other, so they're not going to spend much time, right? It's going to take a lot of oomph to get these two things, because these two methyl groups together, because they're going to clash, stuff like that, and so it's going to spend all of its time sort of in this trans configuration, stuff like that. And so this molecule here is not reactive to this, but if you have something that's locked into this, into the correct configuration, right? This thing is incredibly reactive, and so you actually buy a bottle of cyclopentadiene, you actually don't get you don't get this. You actually get this already sort of pre-Diels-Aldered, if you can sort of think about it. And actually, what you have to do is you actually have to crack. You have to heat it up to crack these two things apart, and if you want to react it further and stuff like that. So this is incredibly reactive because it's in the correct form already, stuff like that. So you have to be careful with that. So when you get it. But that you do see Diels-Alder in biology, right? So here we go. So we have the diene here down at the bottom. Even though it's on the same chain, it's the diene. You have the dienophile, right? It has a nice withdrawing group right next to it, so it's all set up, and you get the there, and you get the new six-membered ring. this comes on here, and you can react it to form this. You can do some other chemistry with it, right there, to form this molecule here. But that's this nice 6-membered ring right there. This one on the right here, for the production of lovastatin. So the statins are all used for cholesterol lowering. So this is actually a natural product. So like that. So this was the first. This was the first one identified. So like that. That was marketed. It's a natural product. Then they went in and then made newer ones that had better biological, that were better drug-like properties. So like that for things like Lipitor, which is atorvastatin, things like that. So Crestor is another one. So like that. They all have very similar structures. They all have this side chain to them. It's called a lactone ring. It's actually 2 alcohols and a carboxylic acid, something like that. So, and then they have different parts down here, something like that. So, but this in biology, so the organism that makes this, something like that, uses a Diels-Alder to make that ring, something like that. So polymers can use this, something like that. So the diene, something like that. So if you're looking at something like isoprene, something like that. So you can get this, you can get these sort of movements around a double bond. So if you have the Z configuration here, which almost looks like cis configuration or whatever, that is, they're on the same side. Remember that. You can get that, and this is the natural rubber. You can also get the more trans-looking one, the E form. This is good aperture, which I believe they used to use in golf balls, stuff like that. So it's the cover of golf balls, stuff like that. And so the problem with this is that they're sort of linear, stuff like that, and they kind of slip, and they're not. It's too soft. Stuff like that. So if you try to make this with just natural rubber on your tires, the tires would melt. And so Harvey Firestone of Firestone Tire fame discovered this by accident. He mixed sulfur and the rubber molecules together. He was trying to throw everything at this, and a little bit of it fell on his stove that was hot, and it was called vulcanized. And what happened is the sulfur was able to cross-link these chains, stuff like that. So instead of just being like this, it sort of made links between the two, and it turns out that depending on the degree of cross-linking, you can actually control the softness of the rubber. And so he was able to make these and make make the longer-lasting rubber tires, stuff like that. So pretty important stuff. Stuff like that. So neoprene is very similar, except it has a chlorine there instead of a methyl group, stuff like that. But it's very similar sort of chemistries for neoprene, stuff like that. So okay, so UV vis spectroscopy, stuff like that. So for this one here, this is the last of the spectroscopic techniques we're going to talk about. This one uses just the ultraviolet light, which is between about 200 and 400 nanometers, although usually it's usually considered UV vis, and so you sometimes go into the visible range as well. You can use this technique. It turns out that most things that have double bonds, particularly conjugated double bonds, will absorb in this sort of 200-ish range, 200 to 400 range, something like that. So, stuff like that. So, like that. But you can come in here and stuff like that. So, what you get, you have this equation here, stuff like that. So, concentration and path length. Okay, so absorbance that you get out. So how much light is absorbed as so you send light through it. You know how much it should be. You know how much came out at the end. So how much did your molecule absorb of a particular wavelength? Okay, so this one here is the molar absorptivity. So this is just a constant for each molecule is going to have its own constant. It depends on how much the characteristics of light for how much is seen. This is the concentration of your molecule, right? So by that, and this last one, which is an L, this is path length. Okay, and so if it's going through twice as much material, right? So if your path length, it's usually 1 centimeter, but if you put 2 centimeters on there, right, it's going to absorb twice as much light as if it just went through 1 centimeter of material, and so you have to correct for that, stuff like that. So it's usually 1 centimeter, but it's mostly stuff like that. So, but it's something to be aware of. Okay, so you can get a question like this, and usually what happens is I give you 3 of the, or you got 4 variables here, right? I'm going to give you 3 of those. You got to figure out the 4th. And stuff like that. And so here we go. So at 340 nanometers, NADH, which is sort of a biological oxidant, so it's a biological H hydride. It's a biological H minus. Stuff like that. So at 340 nanometers, its molar absorptivity is 6,300. So we know what this is. So 6,300, right? So with that, and we're using a 1 centimeter cuvette, so that's 1 centimeter, right? Okay. Oh, I'm sorry. This is per molar per centimeter. Okay. So by that, and the reading came out. So this is how much absorbed. So this is 0.025. That's the reading that came out. That's how much absorbed. What's the concentration of that? So we're looking for that. Okay, and so we know 0.025, right? Equals to 6,300 per molar per centimeter, right? Times the concentration that we don't know times the 1 centimeter path length, right? We can go ahead and cancel out the centimeters, right? So I'm sorry. This should be so per molar per centimeter. Okay. So by that, and so what we're left with is 0.025 equals 6,300 per molar. That's the units times C. So what do you got to do? You got to divide both sides by 6,300 per molar. 300 per molar, right? So C is equal to 0.025 over 6,300 molar, right? So divide, you end up getting it up top. And so it ends up being 4.0 times 10 to the minus 6 molar, which if you want to get fancy, you can say 4.0 micromolar, because micro means times 10 to the 6, 10 to the minus 6. I'll take either answer, stuff like that. So, but what's going to happen is I'm going to give you 3 of these, right? 3 of the 4, and you got to figure out, give me what the 4th is. Not too bad. So like that, it's just some basic algebra, like that. So. Okay, so interpreting these things. Okay, so what you need to know is that basically the longer the stretch the conjugation, so double single, double single, double single, the higher the wavelength that it absorbs. Okay, and so here's, right, so here's 2 double bonds, right? It's 220. The rings make things a little weird, but here it's 3 double bonds, right? So 2 double bonds in a row is 220. 3 double bonds is 258. 1, 2, 3, 4 double bonds in a row, it's 290, right? So with that, and so that's the general trend. Well, when things get benzenes and things get rings, it gets a little weird, stuff like that. But that's the general trend, stuff like that. So that would be a nice thing to remember. That trend is a nice thing to know, and stuff like that. And so for here, right? So biology can take advantage of that, right? So you have beta carotene, right? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you have 11 double bonds in conjugation, right? You're going to get a very long wavelength. So 255, which is orange, right? So beta carotene is orange, right? So there's an enzyme that breaks this apart, so slices it in half, and now neither one of these is orange anymore, right? Because it's now, this one's only 1, 2, 3, 4, 5, it's 1, 2, 3, 4, 5, right? And this one's 1, 2, 3, 4, 5, right? So now there's 2 5s instead of an 11, stuff like that. So, well, that happens, stuff like that. So neither one of these guys shift, now absorbed down near like 300 or something like that. So, but vitamin A and cisretinol, stuff like that. But we can take advantage of these different colors by extending out the chain, stuff like that, to absorb different colors, and that's what we've got.